as we get to the end of the semester, the very last of my chapters here would be X-ray spectroscopy, which again, is fairly non-routine, type of spectroscopy, other than for certain specific industries, particularly, of course, in the medical field. If you're in geology, you're gonna find X-ray spectroscopy. It's fairly important, but also in food analysis and so on. So X-ray spectroscopy is not any different, than the other types of spectroscopies that we have covered. The only difference, of course, is the fact that, you're using, a very energetic beam of electrons, or rather of photons called the X-ray. And of course, you're looking, for the effect of impinging X-ray, on a sample, and the effect would be absorption, meaning you can do X-ray absorption spectroscopy, but the other effect, can also be, the X-ray impinges on the sample, and that causes excitation of the electrons, and there is a relaxation of electrons to give you a photon, and the photon in this case would equally be an X-ray, which would be X-ray fluorescence spectroscopy. And then so take note of that. It's not any different. The only difference is because you're using very energetic beam of the X-ray, then there's a differential type of chemical transition, of course, that is taking place. And that's what we're going to be looking at, in this chapter. What the mechanism of, the chemical electronic transitions, that are taking place within the molecule. So a few basic facts. Of course, you're dealing with a very energetic beam of electrons, and for that reason, we often do not actually measure X-ray in form of wave numbers, but instead, we measure X-ray in form of energies, electron volts in form of energies, okay? Now, another thing is you're dealing with a very energetic beam of electrons, and for that reason, it's damaging, of course, to the molecules, meaning, of course, it's gonna cleave, the chemical bonds and break them, into atoms, and for that reason, X-ray really, is often only largely used for in atomic spectroscopy, because the chemical bonds is too energetic, and the chemical bonds, are broken. And that's why, of course, X-rays are fairly, biologically damaging, because they break down the chemical bonds. Now, as in this slide shows, the components of X-ray spectroscopy are not any different, from other spectroscopic techniques. You need a light source, and of course, the light source needs to be an X-ray. You need wavelength selectors. You need detectors. And in this chapter, we're going to talk about different ways of generating, the sources, the X-ray sources, different ways of using or components for the wavelength selector. Of course, because you're dealing with an X-ray, it's going to need a special type of wavelength selector, and specific types of detectors, that are relevant to the X-ray, again, because you're using a very energetic, type of a photon. So let us start, with different ways of generating, the light sources, the X-ray sources. What is the source? What's the X-ray source, and how do you generate it? There are 4 different types of X-ray sources that you can use, and I'd like you guys, to understand how they are generated, starting with the very first one. Now, if you take a very energetic beam of electrons and you accelerate it, in a very, very high energy, and bring that beam of high energy electrons that's rapidly moving into a rapid stop. Now, what's normally generated actually is an X-ray, or energies that are proportionate to the energy that is lost, because of bringing that rapidly moving particle, into a stop. And that's what you refer to as, the braking radiation, by these German gentlemen. And so it's pronounced as braking radiation. Again, if you take a high energy beam of electrons, accelerate it on a target, and bring it into a stop, the energy that is lost, would be proportional, to the X-ray energies, that is generated. And that is how you actually generate, X-rays, by taking a beam of electrons and bringing it into a complete stop. Take note of these, the braking radiation or X-ray radiation that you generate, is actually a continuum, meaning, it's going to have differential types of energies which are proportionate, to the deceleration, the series of deceleration, that took place, when you took the electron and collided it on a target. Of course, not all electrons, are gonna completely stop, at a specific time, but instead, there will be a series of deceleration, that would be proportional to the type of X-rays, that is generated. So take note of that. Braking radiation is one classic and most important, I think the most common form of the X-ray source, that you can actually generate and use, of course, for X-ray spectroscopy. I've shown you these sort of figure here to show you the different types of things, that can happen when you take an incident beam of electrons and you accelerate it onto a target. Take note of this, the braking radiation can happen, as I've explained, but other things can also happen, that are chemically relevant or useful for chemical analysis. Things like secondary electrons, can be generated. And what I mean by secondary electrons in this case is that primary electrons causes ion or knockout, electrons, from the chemical species, and then secondary electrons, are generated. So essentially, this is ionization can take place. And as you well know, ionization can be a fairly useful aspect in chemical analysis. Remember, in the last chapter, we talked about different methods of ionizing samples for the mass spectrometer, and electron impact, was one of those methods. And you can see, really, this is electron impact, that is actually taking place in this case. Other things that can happen include, scattering. The electron beam incident, can be scattered by the sample, and then you can study the backscattered electrons. And actually, that is a basis, of the SEM, scanning electron microscopy. It is used to monitor the backscattered electrons, which would be relevant in mapping the morphology of the type of sample that you're analyzing. So scanning electron microscopy, which some of you may know about it, is based on that backscatter defect that comes from, sample being scattered, incident beam of electrons being scattered by the chemical species. And that was used for analysis of the morphology of certain types of materials. So take note of that, of other things that can happen, other than the braking radiation. And of course, other electrons, of course, can be transmitted and so on, depending on the type of material that you're dealing with. Now, other than the braking radiation that you can use to generate an X-ray source, another method, that you can generate the source is this one, where you take a primary beam of X-ray, possibly generated by the braking, and then you use it to impinge on a sample, And when you impinge it on the sample, and I'm going to show you that in the next couple of slides, that X-ray, can cause ionization, of your sample. And with ionization of your sample, electronic transitions, within the chemical species can happen, causing generation of X-ray by fluorescence. And I'm going to explain it a bit more clearly in a couple of slides. X-ray fluorescence. And what's happening, of course, within the electronic configuration of the chemical species when it is impacted, by a primary beam of an X-ray. And I'm going to explain it in a couple of slides here. Another type of source that can be used, is a radioactive substance. And of course, you guys know of different types of radioactive substances out there, like nickel 63 and iron. You can have a radioactive type of iron. There is uranium and so on. All those types of radioactive elements, can be used to generate, an X-ray, that can be used as a source of radiation for X-ray spectroscopy. And finally, another type of X-ray source can be the synchrotron radiation. Very, very rare, of course, because it's very expensive. But just for the sake of completeness, I list it here as another type of X-ray source. So very quickly, let me talk about the components of an X-ray source, particularly, when you're doing the breaking radiation. Typically, you would have it like this, which is just an X-ray tube where you've got, a filament, and the filament is generating, the electrons. And as it generates the electrons, you've got an anode here, which is positively charged, that attracts, these electrons, to that anode. And on that anode, you make it, a metal target, of course, is an electrode, so it's a metal target. And, so those very fast moving electrons are brought into a complete stop, generating what you're calling the breaking radiation, which is an X-ray. And that goes through what you refer to as the beryllium window, which is beryllium, really. The fourth element, in the periodic table, is not X-ray active, it's X-ray transparent, and so it won't absorb those X-ray radiation. And that goes, of course, now to your sample. So take note of that in terms of how the X-ray tube actually works. Now, so the second type of source, as I explained, is the X-ray fluorescence, okay? So this is where you take, a primary beam of X-ray, and then you impinge it, on an element, such as shown in this case. As you well know, X-ray is highly penetrative, so it would penetrate, the outer energy levels, and it would knock out, an electron, that is in the inner energy level. And so it's going to knock it out. It's what you refer to as a photoelectron. So that electron in the inner energy level, it is knocked out, creating a vacancy. And the vacancy here is called a hole. Now, of course, because that hole is of lower energy, the outer electrons, would like to fill in that hole. And so they drop, the outer electrons in the energy level, they drop into that hole. And that drop results into a photon being generated, because you can see a photon is being generated. And that photon is what you refer to as an X-ray photon, which will be proportional, of course, to the energy gap, between the vacancy from which it's falling from, into the hole. And that's how, X-rays are generated, using the X-ray fluorescence. So again, it's another way of generating an X-ray source. So take note of this. Because you're using an element, the type of spectra that you get in this case, of course, would be a line source, okay? So in this case, it will be a line X-ray source rather than a continuum, similar to what we had as a breaking radiation as a continuum. But in this case, this is a line source. Again, remember, the X-ray primary beam is interacting with the inner electrons, dislodging it, and then an outer electron falls into the hole that was created, and because of that relaxation, that produces a secondary X-ray fluorescence, which again is a line source that you can use, to impinge onto the sample, for chemical analysis. Now, you would find, these X-ray fluorescence, sometimes they are designated as K, L lines or M lines. And of course, that refers to, the vacancy or the hole that was created, okay? So if at all I dislodged, an electron, in the first principal quantum number, that line is gonna be called, the K line. Now, if at all the electron that was dislodged, the photoelectron is in the second principal quantum number, the X-ray lines, are gonna be referred to as the L lines and so on, okay? And so that's how they are designated, based on the principal quantum number from which, the electrons, was dislodged, by the primary beam of the X-ray. And remember, it doesn't have to be a primary beam of the X-ray. It can also be a primary beam of electrons, because a beam of electrons that is energetic enough can also penetrate and dislodge inner electrons as well. So take note of this, that if at all you've got, smaller atoms, that have got a smaller atomic numbers, they don't have many different X-ray lines, of course, because you don't have many possible transitions, that can take place. For example, if at all you've got a sodium atom, chances are, it will only have the K lines, because you've got only so few energy levels, from which you can dislodge an electron. Now, as the atomic numbers increases, so also are the possible transitions, that can take place. And as such, you can have the K lines, the L lines, the M lines, and so on, which will constitute, the spectra, that you actually get. Now, the X-ray fluorescence, as a source is fairly desirable, as I said, because it's a line source. And because it's a line source, of course, you wouldn't need very expensive type of optics, to make it into a monochromatic beam of radiation. And for that reason, it tends to reduce your background. And if you're reducing your background, of course, which is noise, that tends to increase, your signal to noise as well. So take note of that. The X-ray fluorescence used as a source is fairly desirable because you tend to get a cleaner spectra, because you're dealing with a line source. Now, other than the X-ray, the other type of source, as I mentioned before, is a radioisotope. And the radioactive species, such as iron, nickel, cobalt, and so on, they can be used, to generate a monochromatic beam of X-rays. Now, the problem, of course, with using radioactive isotopes is because, one, they tend to produce very low energy type of X-rays, so the limit of detection for this tends to be poor, because you're dealing with very low energy type of X-rays. However, one advantage of the radioisotopes, is the fact that they can last a very, very long time. And so if at all you're looking, for a fairly miniaturized instrument that you can use in the field, then a radioisotope is a very good source, because they tend to last for a long time, But of course, the decay process is a very slow process, meaning the signals, tend to be fairly small. Now, the other type of source is what you refer to as a synchrotron, which is not practically useful, of course, in a regular lab, because a synchrotron typically is generated, if you take electrons, protons, neutrons, and accelerate them, in an electric and a magnetic field, and accelerate them fast enough up to the speed of light. And when that happens, they tend to generate a beam of X-rays, that is unidirectional, that is in the direction of travel, and that can be very, very intense. I think we got only really one type of synchrotron in Canada, which is in Saskatoon, the so-called Canadian light source, that is used to study the different types of small atomic particles that can be generated, such as neutrinos, and so on. Again, it's not a very practical instrument as far as chemical relay analysis is concerned, but nonetheless, for completeness, I thought it's good to include it here as well. So let's quickly talk about, the different types of spectroscopies out there, the X-ray absorption spectroscopy. Now, an X-ray beam of electrons, when it impinges on a sample, a portion of that X-ray, can be transmitted, and of course, a portion of it, can be absorbed. Now, the absorbed X-ray is only absorbed if it matches the binding energy of an electron in that atom. So if the X-ray, the incident X-ray, matches the binding energy, of an electron, okay, in that atom, then that X-ray can be absorbed. Now, of course, higher energies or higher X-ray energies can also be absorbed. However, that tends to decrease in efficiency of that absorption. So you need a perfect match of the X-ray, to the binding energy, of the electron. Now, of course, if the energy is very, very high, ionization takes place, meaning you get a photoelectron, or meaning an electron, is ejected. So for that reason, you would find X-ray relay is not a very, X-ray absorption spectroscopy is not a very analytically useful technique, because in most cases, you would get ionization or dislodgement, of electrons actually taking place, rather than, just an absorption, okay? And so for that reason, it tends to, not be very analytically, actually useful. As I said, energy of the electrons, below energies that are higher, causes, the dislodgement, of the electrons, but the energies that are just equivalent to the binding energy, then you can get, some, what you refer to as absorption edges, for the spectra, which can designate sort of the type of chemical entity that you're dealing with. But like I said, the signals tends to be very, very small, and it's not very, very analytically useful, although sometimes it tends to be used for very specialized types of applications. Now, X-ray absorption spectroscopy is very similar in terms of its behavior to typical type of optical spectroscopy, where Bayer's law, is followed. You can see Bayer's law, absorption is proportional, to the concentration, and the proportionality constant, in this case, the so-called absorption coefficient in the X-ray case, is dependent, on the density of the sample, but it's also dependent, on the sample thickness as well. Now, X-ray absorption spectroscopy tend to be very severely affected, by matrix effects. Again, that's why I said it's not a very analytically useful technique, other than in very specific cases, such as, analysis of sulfur impurities in hydrocarbon fuels, just because, the sulfur, tends to have very, very specific, K, L, and M lines, and as such, it tends to be useful for that application. Now, for quantitative analysis, X-ray fluorescence is the most useful. Okay, it's the most practical way of doing quantitation. Now, of course, with the X-ray fluorescence, you want the incident beam, to be a lot higher, in energy than that is higher than the absorption edge, of the analyte. Remember what I said before? The absorption edge of the analyte really, is when the binding energy of the electron is sort of equivalent, to the X-ray beam that is heating it. But with X-ray fluorescence, you want a much higher energetic beam, so that you can dislodge, the inner electron. And with that, you get an outer electron falling into the inner vacancy, generating a secondary X-ray fluorescence spectra, which would be which would have a chemical signature, relevant, to the kind of chemical species, that you're trying to analyze. Now, X-ray fluorescence, very, very common. Again, as I said, for chemical analysis, even, and of course, there are different types of X-ray fluorescence, which we're going to talk about in a couple of slides here. And so it tends to be very useful when you're doing X-ray dispersive types of spectroscopy. Take note of this, the excitation or the incident beam doesn't necessarily have to be an X-ray. It can just be a fast-moving beam of electrons. And a fast-moving beam of electrons, again, if it impinges on a sample, it can penetrate the sample and be scattered, and that way you can do SEM, or scanning electron microscopy. But also it can dislodge an electron, an inner electron, and resulting into an X-ray, which you can actually detect using energy dispersive types of spectrometers, and that's why I have it, here. In most cases, you're gonna see the SEM, being combined, with the EDX, so that you can actually do the morphology mapping, as well as get some information in terms of the elements, that are actually present. Now, another type of X-ray spectroscopy, is what you refer to as the X-ray diffraction. Because as you guys well know, if you take a beam of X-rays and impinge it, on a crystal, now the crystal tends to diffract, that X-ray, and the diffraction, is based on the lattice structure, of that crystal. And for that reason, you can actually use X-rays, to determine the type of crystal, that you're actually, analyzing. So it's very, very useful, especially in geology, when you're trying, to differentiate different types of geological materials. And every geological material, would have, a certain types of crystal lattice. And so it's very, very useful, especially for analysis of valuable metals, like gold and diamond and so on. If you shine an X-ray on it, you would be able to tell, whether it's diamond or so on, because different types of crystals have got very specific, types of lattice structures, because of course, if at all you've got diamond, it will be layered like that, and each of them, has got different distances, between the layers, and of course, the diffraction is gonna be dependent, on the d in terms of the distances, between the lattice structures, within the crystal. And so take note of this, that the X-ray is very, very useful as a technique, to do diffraction, of different types of crystals. However, you can also use crystals, as a way, to do wavelength dispersion, when you're doing X-ray spectroscopy. So remember, you need a monochromator, with any type of spectroscopy. And so the monochromators in X-ray spectroscopy, is actually a crystal, because again, crystals, can diffract, the X-ray beam into its component energies. And so you can actually use crystals, as a wavelength selector or a monochromator, when you're designing X-ray spectroscopic techniques. So other than using, X-ray as monochromators, you can also use simple filters, especially if at all you're using breaking radiation. Of course, you need to make it into a monochromatic beam. And you can use filters, such as zirconium filters, which are gonna let through only specific types of, X-rays are going to the sample. So again, simple filters such as zirconium, can actually be used to filter continuum type of radiation, such as the breaking radiation. However, this is for very inexpensive types of instruments, because like we said, even with the optical spectroscopy, simple color filters don't give you very good monochromatic beam of radiation. And so also, things like zirconium filters, again, they do not give you very good monochromatic X-ray beam of radiation. And so instead, you have to use an X-ray, a crystal, as your monochromator, for a good type of an X-ray spectrometer, as I've explained. As I've explained, the diffraction typically is based on what you refer to as the Bragg's equation. And the Bragg's equation, you can see, is really dependent on the D, and the D refers to the distance, between the lattice structure, between the two layers, in the lattice structure. And those two layers, again, they are dependent on the type of material or crystal that you're working with, because every crystal has got a very specific, type of lattice structure. But again, in this case, we are saying that you can actually use crystals, as monochromators, when you're doing X-ray spectroscopy. So let's quickly talk about transducers, different types of detectors that are used with the X-ray. Now, there are three types of detectors that you can use. There's what you refer to as a gas field transducers. There's what you refer to as scintillation counters. And there's what you refer to as a semiconductors, that are very similar to what we talked about before, talking about optical spectroscopy. Now, the gas field transducers, can be operated in three modes. They can be operated either as ionization chambers, they can be operated as proportional counters, or you can operate it as a giga counter. And I'm gonna explain that, in the next slide, which is again is based on, the bias potential that you use in the gas field tube. So if you take a gas field tube, such as this, and fill it, with gases such as xenon, krypton, or argon, and you've got, a cathode and an anode, and you've got an X-ray, penetrating, through the beryllium window into that gas field tube. As you would expect, argon, being hit, by a photon, which is an X-ray, you would generate a photoelectron, which I've already explained, based on X-ray fluorescence. You would generate a photoelectron. Now, this photoelectron, again, is energetic. It will go into ionizing, more of the argon that is present inside that tube. Now, the electrons that are generated are accelerated onto the anode, and the anode is positively charged. And because of that, you'll be generating, current, because of the electrons, that are being accelerated onto the anode. Again, remember, the ionization within this tube really is dependent, on the bias potential, meaning it's dependent on the voltage, that you apply on the anode, so that you can pull the electrons. And as you're pulling those photoelectrons, they go into ionizing more of the argon gas, due to the collisions, that would be taking place within the gas filled tube. So very quickly, the gas field response is again based on the bias potential, that you apply on the anode, as I've explained. If you apply very low type of voltage, it means that the electrons that are generated recombine, with the cations, that are present. So remember that. So you've got that, giving you electrons. And if the energy is not enough, if the voltage is not enough to pull these away, then, you get it recombining and the reaction goes back, to form the argon gas again. And so the energy is not enough, to pull away, the electron that is generated. You can also have a situation like this, where the number of electrons, that are reaching the anode are equal to the number of electrons that are being generated by the primary X-ray. And so you've got that amplification. There's no amplification per se in that case. Alternatively, you can have a voltage that is high enough such that, the number of electrons, that are reaching the detector or the anode are much higher, compared, to the number of electrons, that are initially generated by the X-ray pulse, because you're pulling, those electrons very quickly and they are causing secondary ionization to happen. And you can see this relationship is linear, meaning, for every primary X-ray that you generate, for every primary X-ray that gets into the gas-filled tube, you generate a much higher, number of electrons in a linear fashion. So again, you can see that amplification. There's an amplification, because of the secondary electrons, that are generated from the primary electrons, that are impinging, on the argon as they are accelerated towards the anode. And finally, you've got this other region here where the voltage is very, very high, meaning you're very quickly pulling away these electrons, and it's a very energetic beam of electrons because you're using very high voltage, positive voltage, to pull it away. And as you pull it away, it's colliding with so many of the other argon gases, generating even much more cations. And because of that, the relationship is actually not linear because of what you refer to as a space charge effect. You start getting repulsive effect because you got a lot of ions that are constrained within a very small area within this tube, and so you get repulsive type of interaction, the so-called space charge effect. They take over, and so the relationship is actually not linear, in terms of the number of electrons, per photon being generated. And so based on those different, scenarios, you can actually generate or make different types of detectors, X-ray detectors. For example, if you use very high energetic beam of voltage, if you use very high voltage, as I said up here, then you can make what you refer to as the Geiger counter. So you're using a very high bias voltage. So a very large number of electrons is generated, meaning the detector is very, very sensitive. However, you get the so-called space charge effect, meaning you know that it tends to be pulsated. All right, meaning you don't get sort of a continuum beam of signal because of these space charge effect taking place. And so because of that, the detector, tends to have what you call a dead time, meaning, sort of it's saturated, it's not detecting anything at all. And so it tends to work very well if at all you're dealing with pulses, signals that are pulsated, they tend to work fairly well if at all you use a Geiger counter. Now, if at all you're in the middle region, up here, the linear region, where the voltage is just enough to cause a lot of amplification of electrons, however, not large enough to induce electrostatic repulsion or the space charge effect, then you call that, what you refer to as a proportional counter detector. And then in this case, you can see the amplification factor, is fairly big. It tends not to have a lot of dead time, because you're not getting the space charge effect taking over. And for that reason, it's a very widely used X-ray type of detector. If you use a very low bias voltage, then again, you tend to get the recombining of, the cations with the electrons. And for that reason, you're not generating enough current. And so the detection, the sensitivity is fairly poor. And for that reason, you call this detector ionization chamber detector. Is not very commonly used, because of the poor sensitivity. However, it's been used a bit, for measurement of, it has been used for radiochemical measurement. And Toshiba, actually produces ionization chamber, types of detectors mainly for use in radiochemical measurements. So again, it's not very useful, when you're doing chemical analysis in general, other than, in radiochemical measurements. So another type of detector, that is used is a so-called scintillation counter. And scintillation counter is where you've got a crystal, you've got the beam of X-ray hitting a crystal such as sodium iodide that has been doped with that element. And because of that, you generate, a lot of electrons. And those electrons, are channeled, to a PMT, to a photomultiplier tube. And the photomultiplier tube, of course, you guys well know, is a series of diodes, and that can generate, or amplify the primary electrons, giving additional type of electrons. And so in the end, you get a lot of amplification. So they've said, you've got a crystal, the primary beam of X-ray hits the crystal. You generate the photoelectrons. The photoelectrons are channeled to a PMT. And the PMT, generates the secondary electrons, resulting into a cascade of electrons. And so you can actually measure the current, that is generated. Lastly, the other type of detector is what you call a semiconductor, not any different from the semiconductors that we've talked about, the PN-type diodes, which are silica-based semiconductors. And an X-ray photon can impinge on a diode, causing a photoelectron to be generated, and then you can measure the currents that are resulting, from the generated photoelectrons. So let me very quickly, talk about the different types of X-ray instruments, out there. Maybe the most common type of X-ray instrument is a wavelength dispersive X-ray X-ray spectrometer. And I think I've already mentioned, the EDX. The wavelength dispersive X-ray, is when you use a monochromator, and the monochromator in this case, is a crystal, and of course the crystal disperses, the energies of the X-ray, and then you can use a CCD and so on, to map the wavelengths, that come out. The EDX, on the other hand, you are not dispersing. You do not use the monochromator at all. You're just collecting the energies that are resulting, and you're differentiating them purely based on their differences in energies. So this instrument, as you can see here, is what you refer to as a wavelength dispersive X-ray. It's huge. It's usually very, very big and very expensive, as well. Whereas EDX tends to be much, much smaller, because again, you do not need the optics and so on, such as the monochromators. And so for that reason, EDX is much, much smaller. And we have one in the lab. If we had time, you guys would have played with it. Now, the non-dispersive type of X-ray, again, they are only very useful for very specific tasks. They are not. They are marginally useful for quantitative analysis. This is where you use zirconium filters and so on. And so they are only really useful, for X-ray absorption spectroscopies, which, as I said before, is not very useful analytically, other than to analyze things like sulfur and so on in gasoline. Again, I won't go into details, just because it's not commonly used, other than in these specific types of cases. There are other variations, of absorption spectroscopy such as this, that are sometimes used, to analyze different types of biological molecules. But again, they tend to be very weak in terms of the chemical information that you actually get out of these variations of X-ray absorption spectrometers. But again, it is non-dispersive, meaning I'm not dispersing the X-ray, and I'm just using zirconium filter, in this case. With the wavelength dispersive, as I said, it's a very versatile instrument. It's got very high resolution. In this case, as I said, you've got a monochromator, and the monochromator is dispersing, the different X-rays that are hitting it, and then you are detecting all those different X-rays, either sequentially, all right, or you can use the multi-channel detectors, like the CCDs and so on. Of course, as we said before, sequential meaning you're scanning, and that takes a lot of time. So you would find in newer instruments that are more expensive, you tend to use the polychromators or the multi-channel detectors, so that you can acquire, all the dispersed X-rays, simultaneously, using multi-channel monochromators, or rather detectors such as CCD. Now, with the wavelength dispersive instruments, again, you tend to get very, very good type of resolution. However, very expensive, because you need a series of gratings, so that you can get good dispersion. Advantages of wavelength dispersive instruments, again, you can see greater dynamic range, and you can get good chemical analysis using them. Energy dispersive, on the other hand, as I said, you do not have a monochromator. You're just differentiating the energies based on their different types of energies, and so they are much simpler. You do not have a lot of moving parts and so on, and so you can miniaturize them. And that's why, for example, in the Mars rover, you actually had an X-ray dispersive, energy dispersive instrument or spectrometer there. However, they have very low resolution, and that's why sometimes I use our energy dispersive instrument in our lab here. But if at all I want to get a very good spectra, often I have to go to the U of A to do a wavelength dispersive, to use a wavelength dispersive instrument. But again, if you guys want to play with it or have a look at it, you can let me know and I can take you to the EDX and you guys can somewhat take a look at it. So the kind of spectra really that you get, as I said, is atomic spectroscopy really. So you're mapping different types of elements. It's only really useful for analysis, of elements. And that's why for geological materials, it tends to be a fairly useful type of instrument. As I said, it's only really useful in X-ray fluorescence. So you're looking at X-ray fluorescence in this case. So you can do quantitative analysis using X-ray fluorescence, and you can actually make calibrations as well, but it's a lot more involving, especially in terms of making standards, just because of the matrix effect, and so on. So you have to be careful, in terms of how you actually make the standards with X-ray fluorescence. So as I said, in this case, very useful for geological materials, such as Martian rocks and so on. They can be used for elemental analysis of different types of materials. In fact, I would say, while it's used quantitatively, it's much more useful, for qualitative, analysis. Although, as I said, you can try to do semi-quantitative analysis, but it's better, for just mapping, what elements are actually present, in my sample. Other advantages, it's very good in the sense that you do not destroy your sample, and so if at all you are working with a very valuable sample, such as jewelry or valuable coins or even paint, then really, you do not need to destroy the sample. You just shine an X-ray on it, and then you can get an X-ray spectra of the different elements, that are actually present. So in that, it is a surface technique. It's very fast and fairly precise as well. And you don't need to prepare the sample either, because it can analyze solids and so on. In a minute, disadvantages, and I'll let you guys read it, such as it's very expensive because you need very good types of optics, and the optics have to be crystals or series of crystals actually. And so for wavelength dispersive instruments, they tend to be fairly expensive instruments. Now, quantitatively is not a very great technique for quantitative analysis. You can compare it, say, to an ICP mass spec or an ICP OES. It's not a very nice quantitative technique. Maybe another disadvantage is the fact that you cannot differentiate the different oxidation states, of elements. So it's not like photometry or mass spec, which can give you, for example, the different oxidation states. And I've said before, sometimes it's difficult to do speciation because the speciation can tell you, the nature of the oxidation state of the elements it's in. Yeah, so take a look at, the other disadvantages as well. And that's all that I'm gonna really say about X-ray spectroscopy. As you've seen, it's not different, from the other types of spectroscopies, other than the fact that you use different types of detectors and you use different types of X-ray sources, and I've tried to explain how you generate the different types of X-rays. If at all you like more information about X-ray spectroscopy, you can look at this link here from the Carleton University, and if at all you're really interested, but my notes really have explained well enough what you really need to learn about X-ray spectroscopy. Now, we are getting fairly close to the end, and I assume maybe for most of us, we are getting fairly depressed. However, in the next short chapter that I'm gonna that I gonna give a lecture on. Hopefully, I can get you from this form, to being, fairly happy about the end. So you're getting very, very close to the end of our lectures.